Okay, so I need to show you how to graph things in polar. So here's a polar equation. R is 1 plus cosine theta. Okay, so what does a graph of 1 plus cosine theta look like?
I haven't learned this yet.
Heaven forbid.
No, so you know how to do this if this is a y equals 1 plus cosine x, right?
Yeah.
Like you guys can do that one?
Oh.
What is that? That's a cosine graph, right?
Yeah,
Shifted up 1.
It's a wave?
So if I have a theta and an r, right?
Yeah.
Where's cosine start?
Up at 1.
At a max, right? So here's my midline.
Okay.
That's at 1, right?
Yeah.
And then it starts at a max,
2.
so 2,
Yeah.
and then proceeds
To fluctuate.
wobble-de-hoo,
Mid max, just like that.
right? Okay. Where's this crossing happen in theta land? In other words, where's the first time cosine crosses its midline?
8.
The line. Over 2.
R2. Where's this guy?
5.
5. Where's that 2?
3 pi
3 pi over 2.
and 2 pi.
And that max is 2 pi. Okay, so for polar graphing, you need this chunk.
Just that chunk?
Yeah, you need one period. And you need to go out till, you need at least one, you want at least one period, and you want to go out to at least 2 pi.
Okay.
Cool.
Uh-huh.
In this case, 1 period and 2 pi happen to be the same value, right? So I'm looking at this stuff between 0 and 2 pi, and then we'll talk about what happens otherwise. Cool? So, this is like Cartesian land, but with the wrong axis labels, right?
Yeah. That's all.
So, now I'm going to go over here, and I'm going to make actual Cartesian land.
There it is.
There it is. There it be.
Okay? And I'm going to turn this into a picture in Cartesian land using the transforms from polar.
Whoa.
Now, this gets a little funky.
Whoa.
Wait. What are you doing?
He's going to take the
I'm
coordinates
going to
from
make
that.
this into a picture in Cartesian.
It's going to be a circle.
So one way you could do this is you could use the conversion factors for r and theta, right?
I think it's going to be a circle.
And come up with a relationship between x and y, maybe. And plug that into a graphing calculator and hope.
Okay.
Right? But in general, that thing's not going to be a function.
Okay.
So instead, what I'm going to do is I'm going to plot this thing, my r theta graph, in Cartesian land. The way I'm going to do that is I'm going to split it into manageable pieces. Okay? Just like eating an elephant.
What?
If you had to eat an elephant, how would you do it?
One bite,
One bite
man.
at a time, right? Start with something.
One big bite.
One giant,
One
like,
big bite.
unhinge your jaw.
Anaconda.
Yes, exactly. So, I recommend that you split this into manageable pieces.
Not be an anaconda.
And so it's pretty clear that this piece, right, is just dropping from 2 to 1.
So
You guys
the
see that?
radius goes from being 2 to 1.
Okay, so hang on. So what happened to the angles right there? That's angles between 0
And 90.
and 90. Okay, so I'm in this area here
Yeah.
for this stuff here.
Yeah.
And then the radius goes from 2 down to 1.
Yeah.
You guys see that?
Yes.
So when the angle's 0,
Radius is 2.
radius is 2. So 1, 2, done.
So radius is x.
You guys see that? That's the point. Radius is 2, angle is 0.
Yeah. Yeah.
Right? So I'm going to put a little p there to denote that that's a polar point, right? Okay. Then right here,
Radius is 1.
the radius is 1, and the angle is
Pi over 2.
pi over 2. So when we got to 90 degrees, right, that's me thinking we're going from an angle of 0 to an angle of 90 degrees. I'm getting to a radius not of 2 anymore, but of
1.
1. So this point here is 1, comma, so it's 0, 1 in Cartesian, but in polar,
Okay.
1
Polar is
90.
190.
it's 1, comma, pi over 2,
2.
right, in polar.
Yeah.
In Cartesian, it's 0, 1. And then what's going on in there? Well, it's kind of moving between the two, right? So if it moved linearly between the two, I'd have some kind of a, like an arc. You guys see that? Because it's a little weird, right? Because what's changing is the angle's changing and the radius is going with it.
Yeah.
You guys see that? So you could do a little thinking, but I think you'd find out that up here the
Less.
radius is dropping pretty slowly,
Yeah. And then suddenly.
and then it gets faster. You guys see that? So I think it stays near 2 for a while and then drops off pretty quick.
Right.
So I'm claiming that in this bit it's basically 2, right? If it was actually 2, I'd be drawing a circle here.
Can you solve for where?
Yeah, we could find some point where it went halfway or something. Yeah, that would be reasonable. I'm just going to do something like this. It's kind of with me on that?
But it shouldn't actually go above the point, right?
What do you mean it shouldn't actually
The
go?
radius should be greater than 1.
Yeah, the radius has to be bigger than 1 the whole time.
Until it goes.
So if I think about radius of actually equals 1, that would be this guy.
That makes sense.
And a radius of 2 would be this guy.
Right.
And so as I transition from an angle of 0 to an angle of pi over 2, the radius has to drop from 2 to 1.
Makes sense.
Is cool that?
Uh-huh.
Okay. In my next chunk, this is why it has to be multicolored marker day. Here's my next distinguished chunk, right?
Yep.
So where do those angles live?
Quadrant 2.
For pi over 2 pi. So.
From pi over 2 to pi. So those live in quadrant 2. So that's these angles. And I'm going this way.
Yeah. Getting smaller, so radius is getting smaller.
And the radius lives between 1 and 0 in there. Okay, see that? So if I draw my, okay, so this is what a radius of 1 would look like. That's 1 there. And what's a radius of 0 look like?
Not in the middle.
Origin, right?
Yeah. So basically gets the origins from that point.
Sharp's quadrant.
Yeah, so this has to go from a radius of 1 to a radius of 0 as I go
And it drops.
around this way, right?
Yeah.
So you need to kind of think about
And it
something
drops
like
quickly
this.
and then not so quickly.
You guys with me?
Kind of.
Yeah.
So that's, right?
Oh, so it's going to be a circle. with
That's
the-
thinking, okay, so I'm going to rotate and make this thing shorter as I go. And when I get to 90 degrees, I better be at 0 radius. So I'm going to start at 1, and I'm going to rotate getting smaller.
And then go back to.
And now we need to get another color. So I'm going to talk about this part here, which is quadrant 3.
You go from 0 to 1.
And we're going from 0 to 1, mirroring the thing that just happened. So that one should be easy at least.
I might just let.
It's not hard.
It's a very nice part.
It is actually.
Okay.
Okay, and then last part. Oops.
1 to 2.
Wrong
Go back
marker.
to your original form.
Front marker still.
I'll show you when you are.
Last part is this guy, right? So that's going from 3 pi over 2 to pi over 2.
And it goes back to our original point.
So that's this guy.
Yeah.
And that goes from a radius of 1 to a radius of 2. So I'm thinking, okay, there's radius of 1. I had a radius of 2 circle out here.
So you go 2.
So we need to go increasing to 2.
Cool. So that's
I am so freaking proud of that picture.
that's a really good picture.
Thanks, guys.
It's a good picture.
Yeah, that might actually be the best job I've ever done of drawing a polar picture.
It looks good. No, it's
Yeah,
mathematically
especially
accurate.
like freehand like that.
I know those
Many
those
tools.
circles that are like identifying the 1s and 2s and 3s. Those are like
I kid you not, there's a lot of pressure on this lecture.
no.
Okay, so this thing's called a cardioid.
A what?
It's called a cardioid.
A
The
cardioid?
graph is, or that specific?
Oh, is it because it looks kind of like a heart?
Yeah,
That's how. That's
right. Cardioid would be heart picture.
yeah. Heart. So
Heart
that's a cardioid from a 1 plus cosine.
Yeah.
theta.
So there's a picture of a cardioid and the equation of a cardioid. And then what would happen if I did the next period?
It would be the same.
Yeah, it would trace out the same stuff again.
Yeah.
You guys see that?
Yeah.
So I've really only graphed 1 period worth of this thing, but the
also-
picture is not going to change, right?
You've also graphed all of them.
You guys see that?
Yeah.
So this next bit would be what color if I was,
Blue.
Dark blue.
that would be the dark blue chunk.
The DB row.
Cool? Questions, thanks?
No.
Okay, word of warning.
Yeah. Question.
You want to go first or shall I? Go. What do you got?
I was gonna ask, so if we can take a trigonometric function from the radian land, like the polar coordinates land, and turn it into that, can we take the graph of a trigonometric function on that graph and turn it into polar coordinates?
You certainly could. It would be a lot harder.
Yeah.
Yeah. The easy ones to do are trig functions. Okay, so I gave you this method, right? You draw the picture using shifting rules, and then you kind of fiddle with it a little bit and take it from polar land to Cartesian land. If you want to go backwards, the easy way there is actually just to make the substitutions for x and y. Meaning, if I had my earlier example where I had x squared plus y squared is 4, right? If I want to convert this to polar, I'm just going to look at this and I'm going to think, hey, x squared plus y squared is like r cosine theta squared plus r sine, parentheses, r sine theta squared equals 4,
Yeah.
right? Which tells you that you got r cosine, or r squared cosine squared theta plus r squared sine squared theta is 4. And then you factor out an r squared. So you got r squared times cosine squared plus sine squared.
Which is 1.
Oh yeah, which is 1.
So
Right, so you get r squared is 4, but r is positive, right, because it's a radius.
R is 2.
So that would tell you r is 2,
Which is what we said earlier.
which is what I said earlier, right?
Cool.
Okay, so to go from Cartesian land to polar land, just make the substitutions and fiddle with it algebraically. To go from polar land to Cartesian land, draw the function and then massage it into a nice picture.
Which one of these is the polar graph?
Oh, that's a good question. So this thing is the answer to graph this thing.
In polar?
The
Polar on the
Well, if
Cartesian
you want to
side.
do this on your calculator, you have to
yeah,
switch your
that's
node
a
into
so that's a
polar.
fair question. I would call this a graph of a polar function.
So, would you call something else a polar graph?
No,
So I'm gonna call, is it okay if I call that a polar graph? 'Cause
Sure.
It seems like
that'll work.
a graph of a normal function is a graph, and the graph of a polar function is a polar graph.
Sure, that's reasonable.
I mean, he the title with polar graph.
Yeah, I did make the title polar graphing.
Right.
So yeah, that's probably a reasonable thing to call a polar graph. Personally, I would call it a graph of a polar function, but that's totally semantic difference. So don't sweat it. Cool? Question thing? Oh, yeah, word of warning. If the radius becomes negative,
That's
Then Does it go the
right?
other-
Because
does it go-
like, this is quite clearly, the radius is always positive in this picture, or at least 0. So what if it's negative something?
Can we use absolute value?
You'll go through those angles, but on the other side.
Let's say the-
Let me make one of those.